Uh, all right, very good. My name is Lou Qualls. I am the director of the Endeavor Research Initiative and the FedEx Institute of Technology. And we are putting together a seminar series based on energy and agri-tech research that we're doing within the center. And today is the first of our talks. It's going to be in the energy sector. And we are very privileged today to have Dr. Peterson from Kairos Power to come on board and tell us a little bit about the new trends in advanced nuclear power. Dr. Peterson is the Chief Nuclear Officer for Kairos Power, where he guides nuclear technology review and advises on scientific and technical topics for their reactor technology that they are currently developing and licensing for deployment in the near term. He is also a distinguished professor and holds the William and G. McCallum Floyd Chair in the Department of Nuclear Engineering at UC Berkeley. And something I would say about this is he is probably the most ambitious and successful person I know who's gone from academia into the business world. And I know he's had to learn a lot there, and it's been quite a journey, and I'm looking forward to hearing more about it. So with that, Dr. Peterson, I will kick it off and let you go.
Thank you, Lou. It's a pleasure to be able to speak for this series and to provide some background on the history and current activities at Kairos Power and a bit about where the technology came from. Lou didn't mention it, but he's also been heavily involved within the advanced reactor technology field, and in particular working on molten salt technology. And so he's quite knowledgeable as well. I think that's probably one of the reasons that he asked me to join and to kick off this seminar series. Let me go ahead and share my slides for the talk and get that up in presenter mode. So I am going to be talking about some of the origins behind the startup company, Kairos Power, and then we'll give you a bit of an update on where things stand in terms of the current progress and technology development and licensing for this type of advanced reactor. I also look forward to getting questions, and I am going to try to finish the slide part of this early enough that there will be time for discussion and questions. So to start, though, one of the things at Kairos Power that we've done since the founding in late 2016 is to start our presentations always with a reminder about the mission statement of the company. And the mission is to enable the world's transition to clean energy with the ultimate goal of dramatically improving people's quality of life while protecting the environment. And we note that in order to achieve this mission, we must prioritize our efforts to focus on a clean energy technology that is affordable and safe. Those two attributes are a principal focus. And if we, by delivering energy technologies that meet these attributes, we can address the questions both of climate change, carbon emissions, as well as human well-being. And this is one of the major reasons why nuclear energy technology is so important, is because of this potential. And Cairos, as I'll point out a little bit later, is one of a substantial number of companies which are working to develop advanced reactors, and they've played different roles. And so we'll talk a little bit about how that works. So, but first, let me start with a big picture related to nuclear power and some topics related to waste, sustainability, and cost that I think are valuable to know. And then I'll give some background on more specifically molten salt and molten salt cooled reactors. I like to use this slide to sort of put nuclear waste into perspective, and maybe to start with the bottom line. This is a quote from Michael Schellenberger, which I find quite interesting, which is that nuclear power's waste byproducts aren't a mark against the technology. In fact, they are its key selling point. And if you take a look, a key thing is that in 2021, nuclear energy produced 10% of the electricity used worldwide. It's actually proven at scale relevant to address global energy needs. And that electricity that was generated by using nuclear power largely offset the need to burn coal. Both are base load, and it's energy equivalent to having mined and combusted 1 billion tons of coal. So if you took all of the spent fuel that was generated in 2021 and put it onto the football field at Cal Memorial Stadium, which is just up the hill from where I am right now, it would fill a layer about 1.3 meters deep, which is a remarkably small volume. Of course, it's not, we wouldn't actually go put it on the football field, but this is to put into perspective the quantity of material. And you can compare and contrast that to what a pile of coal, 1 billion tons of coal would look like placed onto that same field. And it's a tall pile. It's would actually be about 230 kilometers tall. And to be able to visualize that kind of pile, not that you practically would do it, it would be a hazard for airplanes, if nothing else, and satellites, by the way. But you'd go ahead and you'd stack it up to the point where you'd have to get out into space to really be able to put it into perspective. So the interesting thing about this used fuel is that today we're not actually sure whether it's actually a waste. In fact, it's quite reasonable to expect that with advanced technologies, we would be able to recycle it and recover substantial additional energy from it. So the key point is that it is practical to store, and we do have high scientific technical confidence that it can be managed in the future, including geologic disposal, which from a scientific and technical perspective is known to be an acceptable approach. I think our key issue today with developing geologic disposal for spent fuel is the uncertainty and actual disagreement about whether it makes sense to place the spent fuel into permanent disposal. But it's definitely a manageable problem, and it is a very small fraction of the cost of nuclear power that is needed to fully fund the ultimate disposition. So if waste is one of the attractive attributes of nuclear energy, let's also take a look then at the cost of the fuel. And this is a summary from the World Nuclear Association of current prices for fuel for light water reactors. Now, we know that the current technologies only utilize about 1% of the uranium. That is, it's mainly the uranium-235 and small amounts of plutonium that'll build up in the fuel in the reactor that are actually fissioned. And so 99% of the uranium actually is not used with today's reactors. That could change in the future. And also thorium is a very good prospective source of nuclear fuel as well. But even with this very small utilization in terms of a fraction, if you take the total cost of light water reactor fuel today, and you convert it into a unit that is used for assessing quantities of fossil fuel, that is 1 million BTUs, British thermal units, and you figure out, based on this cost, how much is it per million BTUs, you can see it ends up being about 40 cents. So we can compare this to what we consider today to be very inexpensive natural gas. In the United States, actually, the prices have been going up significantly, but a year or two ago, you could buy it for as little as $3 a million BTUs. And you can see that nuclear fuel is actually very inexpensive. In fact, it's almost free. The question is then, what is it that makes nuclear power expensive if the fuel is dramatically less expensive than fossil fuel? Because we burn fossil fuel, and there's two parts to that answer. One of them is that current reactors require very large numbers of people to staff them. That's largely because the designs date from the 1960s and 70s, when many things were done manually, and advanced reactors have that potential to dramatically reduce the number of people who are needed to operate the plants. But there's also an issue with construction cost. And I want to put that into perspective. Actually, there's some noise in the background. I'm going to switch and put on some headphones so that people don't have to listen to that. Just a second. Okay, I hope that this is helpful for the background noise. So this is a table and it's a bit of an eye chart, but let's go ahead and dig into it a little bit because it's provides some useful information to try to understand what the costs are associated with the construction of nuclear power plants. And so this is a table that comes from what's called life cycle assessment. That is, these are exercises that researchers do to figure out what are the total quantities of materials needed to build different types of infrastructure so that you can assess things such as carbon dioxide emissions over the life cycle of a technology. And so if you take a look at sort of current reactor technology, this is actually the generation 2 plants that are operating currently in the United States and around most of the world. And these are the quantities of concrete, carbon steel, copper, and other materials that are needed to build, in this case, the green column, a generation 2 pressurized water reactor. And the units are kilograms per kilowatt. And what I've done is I've multiplied this by current commodity prices for these materials. And you can then sum up, and what you can conclude is that the amount of the cost of the raw materials needed to build a nuclear power plant constitutes about $30 out of each kilowatt of generation. Now, the remarkable thing is that to build a nuclear power plant like this today costs more than $5,000 per kilowatt. For the new ones that are in construction in South Carolina at the Vogtle site, they're actually up at about $10,000 per kilowatt. And this ends up being less than 1% of the total purchase price for this kind of reactor. You can compare that to, for example, wind turbines. And in the case of a wind turbine, when you sum it all up, you've got about $192 per kilowatt. And so, and this is per peak kilowatt. If you look at average kilowatt, it's a bit different. And so if you go ahead and compare these numbers, what you can see is that the current purchase price per kilowatt, this is about 11% of the cost. And therefore, if you look at construction of wind turbines, and actually the same applies to automobiles. If you see automobiles, about 7.5% of the purchase price is the raw materials. It takes about 10 times more to convert more money to convert these materials into nuclear power plants than to convert them into wind turbines or into automobiles. This factor of 10 comes from a number of different sources, but there's no physics that require that nuclear power plants be this much more expensive than other types of infrastructure. So the key opportunity that we face is how do we reduce construction costs to be substantially closer to what it is for other types of conventional infrastructure? Because if we could do this, we could see dramatic reductions in the overall cost of nuclear power. So this will be something that I'll come back to in just a moment, but it's an area of opportunity. So how do we achieve these goals? The next thing to talk about is what are the strategies to innovate in advanced nuclear and to achieve dramatic reductions in cost, improvement in safety, reductions in construction time, and reductions in staffing. And so I'm going to point to a few things which I think are key ingredients. There's more things that we can do, but at the top of the list, I would put passive safety. So passive safety is an approach to removing decay heat after a reactor shuts down that eliminates the need for external power supply to do that. That is, it eliminates the need for electrical power in order to run equipment to remove decay heat. The existing reactors that we operate today use active safety systems, and they require multiple redundant sources of electrical power to run pumps that can then remove heat. And removing heat after you shut down reactors is a critically important thing to do, because as the fission process occurs, you build up fission products, and those fission products are radioactive. They release heat. So even after you shut a reactor down, there's still a small amount of heat generation. And if you don't remove that heat, the fuel can heat up to temperatures where you can release radioactive materials. So the development of passive safety is something that's been accomplished over the last couple of decades. All of the new plants that are in construction today and that are being designed today implement these features. So the AP1000s that are in construction at the Vogel site, those are have passive safety features, as well as all of the light water SMR designs that are out there today, like NuScale and BWR X300, and advanced reactors like the Kairos Power KPFHR. So this also simplifies physical security requirements. The other ingredient for innovation, particularly in the space of startup companies, is what we call small modular reactors. The idea is by making reactor units smaller and by increasing the number that you build, you can reduce the amount of money that you need to place at risk to build the reactors. You can move a lot more of the construction into factory type of environments where you can achieve reductions in construction costs. And you can also simplify the safety and licensing for these reactors by making them smaller and making it possible to build them more rapidly. You also get more opportunities to run through iterative cycles and introduce improvements. So going to smaller reactors is definitely a direction that is going to be helpful in terms of enabling innovation. And there's been big advances. Companies like NuScale have addressed some of the key regulatory questions. For example, how many people do you need to have in a control room? And the conventional large reactors, the regulations require 4 people per reactor to be in the control room. So a NuScale 12 module plant in principle would be required to have 48 operators in the control room. Well, NuScale has gone through the work, and their current standard design, which has been licensed by the NRC, requires only 3 people to operate 12 reactors, which is pretty impressive. The final thing to do is this important goal of shifting away from using water as reactor coolant and using alternative coolants such as liquid metals, helium, and molten salts. And in particular, coolants like liquid metals and molten salts are interesting because they enable us to operate reactors at significantly lower pressure and deliver heat at higher temperature. The transition away from water opens up significant opportunities to improve safety and efficiency. So because of the fact that it is possible to innovate in this space, in the United States, there's a large number of companies which have been formed, which are currently pursuing the development of advanced reactors. And one of those companies on the West Coast is Kairos Power. It's spun out from research work done at UC Berkeley, MIT, University of Wisconsin, large amounts of it in collaboration with Oak Ridge National Lab, as well as Idaho National Laboratory. And these companies are pursuing a wide range of different technologies with different goals, because there's many different potential applications for advanced reactors, including some of them which are optimized around more efficient use of uranium and reduction in quantities of waste. The key goal for Cairos, again, is affordability coupled with safety. And so reducing cost is a key objective for the Cairos technology. Now, there's other examples where innovation has occurred, and I do think it's worthwhile in particular to take a look at the example of SpaceX and the Falcon 9 rocket. If we compare and contrast that with the space shuttle, the space shuttle was intended to be a fully reusable launch vehicle. It didn't end up working out to be fully reusable. And it also had an architecture that meant that when you had accidents occur, those accidents could result in really bad outcomes. And a part of that was due to the fact that it has a very large, it looks like an airplane, has a very large airframe. So minor damage in any place in this heat shield can rapidly propagate to catastrophic failure of the spacecraft. And that was what happened in one of the major accidents. The second accident occurred during during liftoff. And the other problem was that this spacecraft intrinsically had to have crew riding with the cargo. And so you didn't get the opportunity to do testing and learn about reliability under lower risk conditions where what you're launching is cargo before you started bringing on humans. All of that resulted in significant complication and reductions in launch rates and very large launch costs. And then the SpaceX, Falcon 9 is actually a great example. The first rocket that SpaceX developed was actually the Falcon 1, a single relatively small rocket engine, just big enough to get a reasonable size but small payload into orbit. And by optimizing first a small engine, the next thing that SpaceX did was to put together 9 of those engines in a larger rocket. This sounds a lot like the strategy that we have for SMRs. And if you take a look at how this has worked out, of course, SpaceX now, the launch costs are now significantly below $4,000 a kilogram. So over an order of magnitude reduction in cost. And today, of course, SpaceX is actually pursuing Starships, which will provide probably close to another order of magnitude reduction in cost for launch. At that point, it opens up the potential to do a tremendously wider range of activities in space, including likely sending humans to Mars. If we can achieve similar cost reductions in nuclear, the implications are tremendous. And as I showed, the numbers indicate that for capital cost, if we can achieve costs per pound in building reactors that are comparable to conventional technologies, that could be as much as a factor of 10 reduction in construction costs. So the potential for large reductions definitely exists. And this is something that we want to think about. How do we achieve similar cost reductions as what SpaceX has done in launch? There's a lot of overlap, a lot of insights that can be drawn. And one of the most important things that SpaceX has done by using smaller rocket engines and iterating large numbers of iterations to get them to work well is to break apart what in this slide we're calling the conventional nuclear development cycle, although this was actually the conventional aerospace development cycle, where the cost of the infrastructure that you wanted to test was so large that you got stuck in the plan and design loop and never got the build and test experience. And this is also a problem. This is an intrinsic problem with building very large reactors that you can address by making reactors smaller. So in the case of what Kairos Power is doing, we're using an iterative plan, design, build, test sequence where we do large numbers of iterations, and that allows us to gain practical experience, not just in getting the hardware to work, but also in how to manufacture the hardware and also how to get supply chains to work to supply the materials and components that are needed for the hardware. So this is the key difference that you see when you start to look at companies like Kairos Power and the basic strategy. So let me go ahead and give a little bit of background now about the origins of Kairos Power, and then I'll also discuss what's going on currently and what we expect in the near future. Now, Kairos Power is a nuclear energy engineering, design, and manufacturing company. We're focused on the commercialization of the fluoride salt-cooled high-temperature reactor. The company was founded late in 2016. Its current staffing is 300 employees. About 90% are actually engineering, trained in engineering. And we're committed to a novel approach to nuclear development that really does mirror in many respects how SpaceX approached the problem, that includes iterative hardware demonstrations, in-house manufacturing, with the goal of achieving dramatic cost reductions, as well as by building and testing the hardware, reaching a level of certainty about the actual costs, which is very difficult to achieve if you just do things on paper or get bids from vendors for equipment and components. The cost targets remain to be competitive with natural gas in the US. As you know, as I showed, the cost of nuclear fuel is a small fraction of the cost of natural gas. So the key thing is to address construction costs, construction schedule, and staffing requirements. And the schedule is driven to enable demonstration by 2031 or maybe a little earlier, so that we can have rapid deployment in the 2030s. The basic elements of the technology, it's a solid fuel, molten salt cooled high temperature reactor. So the fuel is a pebble type of fuel, similar to what's been developed for many of the gas cooled reactors. And today in China, there's a HTRPM reactors, which have started up and are running. They are gas cooled and they use pebbles that are about 6 centimeters in diameter. With a liquid coolant, you have lower circulating power requirements, and you can go to smaller pebbles to enable higher power density. So the KPFHR pebbles are 4 centimeters in diameter, the same size as ping pong balls, and they contain about 16,000 trisoparticles. These are uranium oxycarbide particles that are coated with layers of silicon carbide and pyrolytic carbon, and can go to extremely high temperature without releasing radioactive material. They're embedded in a graphite matrix in the form of a pebble. And so the core of the reactor is actually a bed of the pebbles that is circulated with online refueling in order to add new fuel and remove old fuel. The coolant is this liquid molten salt called Fluoride. It's a mixture of lithium fluoride and beryllium fluoride. And this is also something that Cairos is now working with at scale in terms of testing. So the advantages that you get from using molten salts as coolant are illustrated by looking at the thermophysical properties. And one of the key ones is the volumetric heat capacity of the coolant. This is the amount of energy that the coolant can absorb being raised by a certain increment in temperature per unit of volume. High volumetric heat capacity means that you can move larger amounts of heat with smaller pumps and lower flow rates, which is advantageous. And when you look at the molten salt Fluoride and compare it with, for example, liquid metal sodium and lead, as well as helium and even water, you can see that the molten salt has the highest volumetric heat capacity of all of these coolants and is dramatically higher than sodium and helium. And this results in significantly smaller and more compact reactor systems. The other important attribute is a very high boiling temperature. And so you can see that with a boiling temperature of 1400 degrees C, similar to lead, there's no credible ways that you're going to boil the coolant. So you have intrinsic low pressure in this sort of system. It comes with relatively high melting temperatures. And so this is something, controlling for freezing is something that you have to take seriously in developing all types of molten salt reactors. And finally, the fluoride salts are intrinsically highly chemically stable, and they also have substantial capacity to absorb fission products or radioactive materials. And these are also attractive features, particularly compared to the highly reactive coolant that you have with sodium. And so these properties enable one to design reactors that can have very high thermal power output per unit of weight. That's the major reason that molten salts were the most studied coolant for aircraft nuclear propulsion. And also it allows you to output heat at very high average temperature, which gives you high thermodynamic efficiency. So the technology builds on a base of university and national lab research that occurred, particularly starting in 2012, when the Department of Energy funded a set of integrated research projects that focused on this question of moving to solid fuel molten salt cooled reactors. And so key things included, both at Oak Ridge and at UC Berkeley, a set of design studies that came up with conceptual designs for molten salt cooled reactors that could be used for analysis and design, comparison of different design options, as well as developing and establishing a variety of different experimental methods and testing methods, both focused on fuel as well as materials and the behavior of materials under radiation, and then also on passive safety and the thermal hydraulics, the ability to remove decay heat using gravity-driven processes. Also, this work convened a set of workshops that addressed key questions such as, how would you license this class of reactors? The conclusion was that you could use similar approaches to what we use for light water. And I see that George Flanagan is one of the people that's listening in on this talk. Really critical work being done during this period as well was looking at the regulatory requirements for reactors that existed at the time. In particular, there's a set of things that are called general design criteria. It's an Appendix B of 10 CFR Part 50. And if you go through and review those general design criteria, there's a bit over 60 of them. What you find is that they are specific to water-cooled reactors. So the work that was done, George and Jim Kinsey and other people, was to go through these requirements and figure out what the intent was, and then say, what would be the corresponding requirement that you would want to have for a non-water-cooled reactor that would use sodium or helium or another coolant, and develop a set of advanced reactor design criteria. Well, the availability, those have actually been through the process of being approved. There's now an NRC reg guide. The availability of those design criteria was one of the things that made it possible to conclude that you could now license this class of reactors. We also concluded that you could largely use existing modeling and simulation tools, of course, updating and changing thermophysical properties, and that there were viable combinations of materials that could work in these environments, including the fact that you could use 316H stainless steel as a structural material in this temperature range, and it would be compatible with the chemistry that you have with the fluoride salts. So at Cairos, we recognize the importance of performing extensive experiments and using the iterative process. And so we sequentially deployed a series of laboratories. The R lab is focused on non-FLIBE testing. So using both water and heat transfer oil as simulant fluids, as well as non-beryllium based salts to study and qualify hardware to work under the salt conditions. S-Lab is a FLIBE lab also located at our Alameda facility, where we perform testing for corrosion thermophysical properties with the prototypical salt. T facility is located in Albuquerque. That's where we do large-scale component testing, manufacturing, and that's where our engineering test unit is, which I'll show you in just a moment. And in the future, we'll be deploying the user facility, U facility, which will be where we will actually train, we will deploy and then train operators for full-scale commercial plant using full-scale commercial hardware that is electrically heated. This is another way to represent the iterative process: plan, design, build, test, gain insights from test experience, plan, design, build, test, gain insights. The first step at large scale is what we call the engineering test unit. This is a small reactor scale version of an FHR currently in hot commissioning in our Albuquerque T facility. The next step is the Hermes reactor, which is a 35 megawatt reactor design. The construction permit application is currently in review by the US NRC. This leads to then the demonstration of a commercial scale plant. So going from 35 megawatts up to about 325 megawatts, leading to and this is non-nuclear testing of the same kind of hardware to then enable a commercial scale demonstration. Current facilities for Cairos, we have our headquarters, R Lab and S Lab, located in Alameda, California, at the former Naval Air Station that's on that island. We have our T facility, which is in Albuquerque, New Mexico, near to the airport. We also are currently synthesizing at large scale, industrial scale, FLIBE, which is going to be shipped to Albuquerque in an Elmore facility. We call it the MSPP, Molten Salt Pilot Plant. We also have instrumentation testing laboratories in the Northeast, licensing office in Charlotte, and equally important, we've acquired land and we are in the process of completing all of the licensing work to get the construction permit for the Hermes test reactor that will be located in Oak Ridge, Tennessee, at the former K33 gaseous diffusion enrichment plant site. So let me tell you a little bit about engineering test unit because you can learn a bit about our technology as well. So this is actually August of 2021. We acquired the property. We actually started construction on the T facility in very early 2021. By August, we had completed the building, and here is our CEO, Mike Laufer, talking with the Secretary of Energy, Jennifer Granholm. And then in a one-year period, we completed the construction and entered into the hot commissioning of the engineering test unit. This is a Hermes-sized non-nuclear testing facility, the full-scale reactor vessel, primary heat transport system. Because we don't have fission heat generation, there's not a heat exchanger hooked up to it. There's actually a small heat exchanger hooked up to it. And this has all of the capabilities for recirculating pebbles, for inserting and removing control and shutdown elements, for primary salt pump to circulate salt. All of those things are present in this facility. Here's the vessel arriving in November of 2021, being set up. And so you can see the pace at which construction has proceeded for us to be today in the hot commissioning. This is some views. So this is installation of the graphite reflector structure into the engineering test unit. This is one of the reflector blocks being installed. This is a view down into the vessel. So you can see this is the volume that serves as the core. The coolant comes down through a downcomer and then comes up through the center of the pebble bed core. And of course, the top part of the reflector structure in this photo is not yet fully installed. And we've also manufactured 30,000 pebbles to go into this, and they are sitting there in the ETU as well at this point. And the manufacturing of these pebbles from matrix carbon has allowed us to also develop basic manufacturing capabilities that can be applied or for fuel pebbles as well. So this is the control room for the ETU, and this is during hot commissioning. So you can see view infrared, a lot of trend lines for temperatures and such, and then all of the different control panels here. The other thing that we've implemented is that we are also prototyping autonomous or semi-autonomous operation. And so this is the remote control room in Alameda, California. It has access to all of the same data that is flowing into the ETU control room, and it provides us a capability to actually remotely perform certain types of operations for this facility. And so we're prototyping a lot of the things and controls that ultimately will be then demonstrated in the Hermes reactor and then will translate into the subsequent commercial plants. And here's a nice view from the viewing station out over the engineering test unit. This is, I think, this is during hot commissioning, because you can see we've got installation installed, and you can see major upper head components, control element drives, shutdown element drives, primary salt pump, and then other instrumentation type of components that we're using, because this is a heavily instrumented experimental facility. So that's where things stand. Going forward, we are in the process of licensing the Hermes demonstration reactor. It's a non-power reactor, so we're not attempting to make electrical power. The heat will be rejected to air. The design power level for Hermes is 35 megawatts, which is about 1/9 the planned power output for the KPX commercial unit, which will be about 320 megawatts. That factor of 9 is sort of a magic number. It's logical that SpaceX scaled by a factor of 9, going from Falcon 1 to Falcon 9, and there's a moving up by nominally about an order of magnitude is about the right step to take. So at any rate, the Hermes plant is now in licensing. In fact, I think I can show you in terms of the status. So the construction permit was submitted and accepted by the NRC, the application. The whole application was available to the NRC in November of 2021. It consists of a preliminary safety analysis report and then quite a bit of supporting documentation, including topical reports. And then also an environmental report was submitted as well. NRC has committed to a schedule to issue the construction permit by October of 2021. It's supported by a set of 11 topical reports and technical reports. About 8 or 9 of the topical reports at this point have final safety evaluation reports in place as well. This is actually pretty exciting. If you go to the NRC website, you can actually find the dashboard for their progress. So the NRC has completed its draft environmental impact statement, and we're holding a public meeting actually November 16th to get public input. NRC completed that draft environmental impact statement and submitted it into the Federal Register 6 weeks ahead of schedule. So we're actually ahead of schedule so far in the process of NRC review for the construction permit application. Hopefully we'll be able to stay there. It helps in this process to have a reactor technology which has tremendous fundamental safety characteristics. That is, failure threshold for the fuel about 1600 degrees C, so well above the melting temperature of steel. Peak temperatures in accidents under 1000 degrees C, and so several hundred degrees centigrade thermal margin to fuel damage means that in accidents, the focus is not on when will fuel fail, which is the conventional thing you focus on in water-cooled reactors, is the initiation of local failure of fuel, peak cladding temperature, those sorts of parameters. In the case of FHRs, fuel failure is not a design basis, it doesn't happen, and instead your focus is on the integrity of the reactor vessel and the structural integrity of the reflector structure. And those are, in all respects, almost all respects, easier things to understand and predict than local failure in fuel is in light water reactors. That simplification in dramatic reduction in source term, so that your mechanistic source term really depends only credits the integrity of the fuel and coolant in terms of and no credit for the reactor building. The ability to do that and to have a very simple and robust safety case, I do think makes it easier for the Nuclear Regulatory Commission to keep on schedule and move through licensing more rapidly compared to reactors where there are real accident sequences that can be concerning. So with that, I think I've covered pretty much all of the material that I had prepared. I did want to leave some time for questions. I will stop sharing and we'll look forward to the discussion. So please, questions or discussion, I'm happy to cover. We've got probably about 15 minutes or so.
Well, very good. First of all, thank you very much for that presentation. I know for me, being kind of a nuclear guy, I'm familiar with a lot of the technology, and I'm really kind of geeking out over here, to be honest with you, because for me, I spent a whole career in nuclear in which we've never seen this type of specific progress being made, right? Think about that. My whole career, we really haven't built new reactors, and finally, it's starting to happen, and it's happening from the commercial sector. So thank you for your leadership for that. I'm going to kick it off with a couple of quick questions, and then we'll open it up to others to ask. One is, you talked about alignment with regulatory practice, and it's like a large ship, I guess, you're trying to continually turn to align. There's been a lot of retirement from the NRC folks, so you have a new concept and a new group of people that you're working with. So tell me a little bit about the strategy to keep those things moving forward, design, regulatory practice, you have to make it up as you go. So how are you approaching that?
Yeah, so Lou, that's a really good question. I think when you have a strategy of iterative development where you're actually building and testing hardware, you very rapidly begin to realize that manufacturing new hardware and getting it to work is no trivial exercise. It's hard to do that. And basically, there's so many things that can surprise you that when just as one example, stainless steel is a fantastic structural material for these service conditions. It works well in this temperature range. It has excellent properties. However, when you look at manufacturing things from stainless steel unfortunately has a pretty low thermal conductivity. It's got a pretty large thermal expansion coefficient. So when you weld anything with stainless steel, it's the first time you try it, it's going to distort, and you're going to have to iterate until you can get it. You have to worry about residual stresses. There's just a whole set of practical things that you encounter as challenges when you are manufacturing and testing, and it's impossible to anticipate all of them in advance. Likewise, when you're building stuff and you're in the process, what you discover is that there's a lot of things that looked easy in the CAD model to do, but the actual installation and getting everything hooked up can be significantly more complicated, and you end up needing to do a fair amount of field engineering. Now, if you go back to World War II and the period after that, when we were building the first generation of plants, in the United States, our competency back then to build large-scale industrial systems and hardware, frankly, was far better than anything we can do today in most areas. I mean, just the practical capability. I mean, we have really wonderful tools and stuff, but we offshored a lot of the types of things that we used to be able to do well. And rebuilding those skills is challenging. So the key thing is the ability to introduce changes in your design, especially to do the field engineering, requires that you take a licensing strategy that anticipates the need to make those changes. And so the first thing that I would observe is that we developed a combined license approach to address challenges we had with the sequential construction permit operating license approach for earlier plants. I don't think that combined approach works for first of a kind construction. I think we've seen challenges in the Vogel project, and I do think that using a two-step process is essential so that you can introduce those changes. Therefore, the key thing in working with the regulator is to work through and understand what it is, how it is you can implement changes going as you're progressing. It helps a lot to have a simplified safety case, and therefore to reduce the fraction of equipment which is safety related, because that means that when you're making design modifications, you can rapidly screen the non-safety stuff for design changes and implement the changes, and therefore keep on track. The safety related stuff, you have to be a lot more careful in how you implement changes, but at least you can anticipate those and be ready to do it. The other thing that's critical is that non-water cooled reactors are different from water cooled reactors in key respects. I would go back and highlight the work to develop the advanced reactor design criteria that the national labs largely conducted. And George Flanagan, that effort was really critical in making it much easier for advanced nuclear companies to develop principal design criteria. And then what your PSAR and FSAR do is they demonstrate systematically that how it is you're going to accomplish each of those principal design criteria. And then the PSAR feeds into your system design descriptions, your system requirement documents. And so being able to map those all together is the other critical thing in terms of that fundamental fact that you're going to be doing a lot of field engineering. You're going to be making modifications to the design of components so that you can manufacture them. You can't anticipate all of that up front and put it in a CAD model. Therefore, that flexibility is a critical thing. It's much easier if you're working on smaller scale reactors as your first iteration, because it's just easier to build things that are smaller. So that would be my insight on that question.
Okay. The next question I had was, when you're up and running with the KPFHR, how frequently do you think you can be putting them online on a per year basis?
Oh, that's a very good question. So our goal is to be able to rapidly expand the number of deployed KPFHRs in the 2030s timeframe. That's basically because that's sort of the timeframe to get to the commercial scale demonstration. The rate at which you scale, of course, is an important question. And I'm not going to give any specific answer at this point, in part because, I mean, Cairos obviously is going to have goals, but I do think that there's some interesting lessons from SpaceX. There's a very interesting recent interview with Gwen Shotwell at Stanford. And then also Elon Musk has talked about this in recent interviews. And the interviewer from Stanford asked Gwen Shotwell, we see you testing down at Starbase these, prototype launch vehicles, and they fly up and they move around and then they come down and then they blow up. Isn't that expensive when you're constantly blowing up your hardware, And Shotwell's answer is really, really interesting, because she says, actually, that's not the challenge. The challenge for SpaceX, they consider their big challenge being how to achieve the manufacturing capability to have high production rates, because their goal is to build enough Starships in order to make it feasible to move to Mars, right? And that capability to produce in a serial way large numbers of pieces of hardware is challenging. So what Musk will say, because if you think about testing, well, if your goal is to be able to make a lot of copies, damaging some things in the testing is not a problem. And so Musk put it a different way. He said a high production rate cures many ills. So if you think about that capability to make in a serial way large numbers of whatever your hardware is serially, then that supports a fairly rapid deployment rate, which is the correct goal to have. So I know that's not a complete answer, but at least you can discern there's a bit of a strategy there.
Yeah, very good. Very good. Thank you. We'll open it up. Anybody online want to ask any questions? I think, Rami, they can just unmute and ask, right?
Yes, I believe Dr. Aller had a question.
All right.
Turn my microphone on. Yeah, I want to ask the broad political question. So you're obviously in touch with the NRC, and regulators are coming online that are younger people and presumably more receptive to nuclear energy. But the political world is scarcely aware of the need to move towards nuclear energy, as far as I can tell. Well, what do you anticipate in the way of limitations on the NRC's adaptations that will be coming from political sectors?
So, I'm actually cautiously quite optimistic about that question. The first point is that the NRC has recognized the issues that it's had in the past. And so a large part of our ability to progress rapidly is that the NRC has consciously been working to prepare itself to work with advanced reactor developers. And I would cite the AR, the advanced reactor design criteria as being just one good example of the NRC working internally. So they've been very constructive in meeting their commitments around schedule to return. We have multiple final safety evaluation reports. The critical thing is that the applicant needs to get their stuff in on time. And that's not every applicant. So, you've got some applicants that aren't really hitting the bar in terms of the quality and timing of their submittals. You can't expect the NRC to then, take responsibility for those questions. More broadly, in terms of support for nuclear energy, I think that there is a sea change occurring. The recent world events have really
helped
highlighted. Yeah. And the United States during the Fukushima accident and shortly afterward, the president was getting very competent scientific and technical advice out of the national labs through his science advisor and through his Secretary of Energy, Stephen Chu. And so the United States went down a very different path from Germany. You know that Germany, that was what triggered a seat,
Yeah.
and now Germany is suffering horribly.
Yeah.
So we're just sitting back being grateful, I think, at this point, that we didn't do things like Germany did. And I think that that's further solidifying the political support for nuclear power. It's a majority of the public, and it's certainly a majority in Congress that supports the development of nuclear power, particularly domestic ability. So it's more on also the vendors to be competent. I'm very skeptical of paper designs because I've seen firsthand that there's a lot of additional work after you just got a nice, pretty CAD model before you have functioning hardware. So anyway, I think I'm cautiously quite optimistic that definitely the political support is there, and that the Nuclear Regulatory Commission largely, not everywhere, but largely is focused on being a competent regulator that is performance-based. And they're doing a remarkably good job.
Good. And you're entirely non-governmentally funded at this point.
So we actually have received, we have partner, basically we participate in a variety of different DOE funded projects. And we also are a recipient of a risk reduction award from the DOE to cost share the construction of the Hermes facility. But our progress is not gated by the federal funding. That is, we have sufficient private funding that our schedule is completely independent of receiving funding from the DOE, which is a good thing. And appropriations is a pretty unreliable thing.
Thank you very much.
Yeah. Very good. Okay, maybe I think we have time for one more question.
Okay. Any takers?
If nobody else will ask it, I'll ask, what do you think about competition from overseas that may actually help speed this process along?
That's an excellent question. I think that in the United States, if you look at our national labs, our universities, and our Nuclear Regulatory Commission, and our ability to take a performance-based approach, that we have the most credible prospects of developing new reactor technologies that honestly change the game. If you look at particularly like China, in China, there's not that capability to allow innovation to happen and to take risks associated with doing things that have not been proven someplace else already. And also, I would say the same applies to some degree in Europe. That's unfortunate because we need innovation globally in this field, but I think the United States is uniquely positioned actually to develop new reactor technologies, which are honestly different from what we've done before in the ways that will make a difference in terms of making them economically attractive and readily deployed and scaled to larger scale.
Yeah.
Great. Okay.
All right, very good.
All right. Thank you,
So-
Dr. Peterson. Yep. Blue, go ahead. Sorry.
Yeah, I wanted to thank you very much for excellent presentation and great discussion. And it's important for us here in Memphis because this is activity that is centered largely around things going on in the state of Tennessee. And we're very interested in how we can integrate with that and help you be successful. So thank you so very much for kicking off the series and giving us such a great talk.
Thank you, Lou. It's been a
All right.
pleasure. Take care, everybody.
Thanks. Thanks all for attending. We look forward to seeing you at our next talk in November. Thank you much.